Second.
Okay. Yep.
And hey, so welcome everybody. I'd like to introduce Aymeric Rousseau from Argonne National Lab, who's been modeling our entire transportation system. I think that's about a broad scale. You're welcome.
Thank you, and good morning, everyone. Last November, we discussed transportation decarbonization, focusing on technologies that impact individual vehicles. Today, what we're going to be discussing is larger scope, right? Looking at the entire transportation system. So, quick reminder, discussing what our department does. We have multiple groups. We are focused on transportation decarbonization, looking at electrification, connectivity, automation, whether it's vehicle control or transportation system control, looking also at large-scale deployment, looking at more choices. So how do technology impact how people and goods move? Where do people live, for example? All of this is, as you will see, in a coherent and flexible integrated framework. So the mission from our departments.
Oh, Aymeric, I think you're moving your slides, but we cannot see it.
You cannot. I am not moving slides.
Now we can see that. If you just zoom in, then it should be fine.
Okay, sorry about that. Okay.
Perfect.
Yeah. Our mission is to look at transportation decarbonization at the system level. And so the way we're looking at this is better vehicle. So looking at electrification, control, lightweighting. Now these vehicles are getting smarter, right? So we have now vehicle-to-vehicle connectivity. You can buy some vehicles, you press a button on the highway, the vehicle drives by itself, moving to cities right now. And now the roads are getting smarter as well. The infrastructures and traffic light signals being connected. So there is a lot of information around that makes the system, potentially more efficient. But when you're looking at it at the entire urban area, right, the travelers are getting smarter. So the way people move and good moves now is very different than 5 or 10 years ago. So because of the penetration of technologies, we can expect that people and goods movement in 10 years, 15 years will be very different as well. So this is, our entire focus. We've developed a series of system simulation tools. Some developed internally at the vehicle and smarter vehicle, or POLARIS. Some that we're using from, the third-party vendors like PTVVC or Emson. So when we're looking at the end-to-end system simulation, right, when we want to look at, and as is the focus of today, when we want to look at how people and goods move over a very large metropolitan area, think about 100 mile by 100 mile, 3 to 4, 5 or more million people moving and goods, lots of vehicles, lots of traffic lights, lots of roads, lots of buildings, lots of different reasons why people move. That is a pretty big task. Now, we just don't want to understand how people move and how goods move, but what is the impact on traffic flow? What is the impact on energy, on emissions, on greenhouse gases? How can we, for example, use energy efficient routing throughout the system? What does that do, right? If everybody does it at the same time, who's being penalized? Under which condition do we have an optimum system versus a local minimum? So over the last, probably 2+ decades, we've been developing this series of tools. And so again, last November, we discussed the vehicle side on including connectivity and automation. Today, I will discuss the metropolitan area transportation system. So what is POLARIS? At a high level, POLARIS is an agent-based transportation system. So what it means is that everything in the system simulation is an agent. People are agents. Vehicles are agents. Traffic lights, sections of roads, buildings, anything and everything is an agent, and the agents interact with each other. That means that, for example, if it's early in the morning, you would potentially thinking of going to work, but you've got some information that say there is an accident on the highway. Well, maybe you're delaying and you still go to work later. Maybe you're not going to work anymore. You work from home, or maybe you won't take your car and you'll take transit. So everything that affects behavior is one of the key critical components of Polaris. So some background information. Polaris was initially funded by FHWA, I think like about 10 to 15 years ago, and has been going through significant developments over the last 7 to 8 years under DOE Smart Mobility Program funding. And the idea behind here is, how can we make current modes more efficient? So if I'm driving in a vehicle, how can we make traffic flow better, congestion less? But also at the same time, how can I improve the overall system by taking some vehicles off the road? So increasing, for example, transit ridership. How do we incentivize maybe multimodal travel, where people will take Uber or Lyft, like a ride hail, or they'll take micromobility devices to go to transit. So a lot of this is integrated into, again, a single coherent platform. A lot of the similar tools have multiple bits and pieces, which means that they are very computationally intensive. I'm not saying Polaris is not, but it is a lot less than any other software that is looking at entire transportation system. Another piece of it is we're including urban science. So, and how technology impacts how people use their vehicle, but also where do they live. So for example, I gave you mentioned that adaptive cruise control is becoming more and more mainstream on latest production vehicle. You go on the highway, you press a button, car drives itself. Well, what does that mean is that someone is renting a car in a densely populated area. Well, now that person can have a bigger house in the suburbs because the car may drive itself, right? Or if someone has, which actually was one example from the director at the big OEM in Detroit, he said, well, now I'm going to my lake house a lot more often, because on Friday, right, it's 5 o'clock, I go in my car, go on the highway, press a button. 2 hours later, I'm in my lake house. I didn't used to do that as often. Now, almost every other weekend I go there. So it changes behavior, right? Where do you live? How do you travel? How often you travel? How far do you travel? So there is some, not all technology has positive impact. There is some unintended consequences, and that's really what looking at system of system allows us to do. So if we start digging a little bit deeper as to what is a transportation system simulator, based on land use, and we're using Urban Sim developed by UC Berkeley initially, that is used by several metropolitan areas, right? We can then estimate some long-term choices. So what is the population distribution right now, and how will it evolve, right? Do we have, is that person single, married, how many kids, how old, where do people live, right? Where do people work? And then based on that, and also their level of income and a lot of their information, what is the household vehicle choice? Do I have one vehicle, two vehicles, no vehicles? And then based on the number of vehicles, what is technology? Do I have an electric vehicle? Does my vehicle have ACC? Again, looking at market now and in the future, who will own what? Then we go from long-term choices to mid-term choices. So what do I want to do tomorrow or today, right? Do I want to stay home? If I saw, like, how often, how many times per week? Can I do that? Do I want to do that? And then for the day, at some point, right? What do I want to do? I want to go to work. Do I want to go shopping? Do I want to go, exercise, so on and so forth? And then there is a within the choices. So this is what I would like to do. Let's say this morning, I would like to leave my house. I'll go to work, and then I'll go do some shopping and come back. But during the day, right? It's a lot of the, as I mentioned, what happens will impact you, right? There's a lot of traffic. Well, maybe now I won't go shopping today because it will take me too long, and I won't be able to be home in time for dinner. Or there's something that you have to do. I have to pick up my kids, but there's something that you want to do, and maybe depending on some external events, you change your mind. Now, let's say I want to go to work. What's my routing? Again, depending on traffic, we may take the highway, or we may take some small roads. We may take a combination of them, and then obviously this is all impacting everything, right? So once we have all that information, on mobility, we also need to understand, well, now and in the future, if I have an electric vehicle, where are my EV charging stations? If I charge at home, well, that's okay. My in-day may be okay. Do I need to do public charging during the day? If I'm a ride-hail company, that's something I will want to do. Well, where are they located? How does that impact my business case? And then all of this, right? So Polaris is on the mobility side, but now let's say I want to understand what's my energy consumption. So we're using autonomy, which is another one of our tools to do that. Now I want to be able to look at greenhouse gases because I want to minimize this. Well, now we have grid that is also combined with that. Well, I want to look at the equity. Well, we know the information of every single household, so that means that we know where are the underserved communities. So we know the impact of policies on these underserved communities. I'll show you some examples of that. So this framework allows us to answer a system of system questions, looking at mode choice, looking at eco-routing, looking at impacts of driver behavior, looking at electrification, connectivity, automation, and their combination of it. So, 1 + 1 does not equal 2. We know that. It is in some cases, but it is, actually probably an exception more than the rule, because when we're looking at making the system more efficient, a lot of the technologies and policies, will address the same type of inefficiencies. So Polaris is not just a system simulation or workflow, integrating the workflow like I will mention. It also has a lot of set of tools for transportation system analysis. So for example, network editor. So when we work with cities, we need to know where are the roads, where are the intersections, what is the maximum speed, minimum speed, what type of is the stop sign or traffic lights. And you're thinking about it, it's like, data is never as good, right? So we need to be able to fix some of the data that even the cities are providing us. Now, the other reason to have this type of additional tools is that what happens 10, 15, 20 years from now, right? So we're looking at now, well, let's take an example. I'm going to add rapid transit bus lane to some major arterial in Chicago or Atlanta or New York, right? So what that means, that's like my roads are the same, but now my traffic lights are different, right? I need to change that. Well, now I don't have a two-way, I have a one-way. And, maybe, so I have some dedicated lanes instead of having maybe, 2 lanes for cars. Now we have 1 for bus, 1 for car. So all of that can be done through the network editor that we need, sorry. So we need to be able to have all of that flexibility included. The second is obviously, analysis. We run more and more simulations. So usually, right, say a single run is a couple of hours. We run hundreds of them. Well, that means there's lots of data to be analyzed, lots of metrics to be considered. That means the post-processing also need to be developed for that. So the next step is what inputs do we need, right? We have models for 7 to 8 large metropolitan area in the US. We are developing new ones, working with local partners. What does it take? It takes a lot of inputs because, we want to make sure that we properly represent specific metropolitan area. That means we need inputs for population, vehicles, and land use here. Right. So where do people live? What is their employment? A lot of census data that is going in there. We also need to understand where are the different buildings. So are we? Is that a school? Is that a hospital? Is that a large factory? Or is that a single house? How big are they? Right? How many people can be in there? Do you have a garage? So on and so forth. And then how do people travel? So that's where a lot of the behavior, is important. And we use a lot of survey data, going from A to B, how do people route? Who is driving alone in their car? Who's, driving with someone else? What are the different commuting patterns? Who can work from home and who cannot? And if people work from home, when do they actually do it? And how often do they do it? Why on a specific days they stay at home and one specific day they drive? Is that the weather? Is that just Monday, Friday, you stay home, and Tuesday, Wednesday, Thursday, you go to work? What are the vehicle distribution? Who owns what vehicle, what age, right? We want to look at the impacts of energy and greenhouse gases. That means we need to understand today's vehicle fleet and its distribution, not just powertrain, but also age. Then there is a lot of inputs on the network. Looking at my transit network. So that's looking at Chicago, for example. Here, there's multiple transit agencies. How are they connected? What is the frequencies? How many buses do I have when? How do they change on the days during and on the weekends? Where are my traffic signals? Who's controlling them? Are they connected or not? Are they coordinated or not? Some of the traffic signals in Chicago are from the 70s, believe it or not. They are tuned by hand once in a while. But now more and more, we see a lot of connected signals being deployed on some key areas. Well, which area are the most impactful to deploy these connected vehicles? Connected signals, sorry. Are the connected signals connected with some vehicles, for example, on the rapid transit bus lane? If so, how many buses and how many signals do we have? What happens if we go from 100 to, let's say right now we're at 14% in Chicago. How it happens if we go to 50 or 100%? Where are the taxis and ride hail connect? Where are the pickup and drop off? How many do we have? Where are the charging stations? Where are the parking? And you can go on and on and on, right? We need to represent the system beginning to end. Then the last piece of
this.
Yes.
There's a lot of information here, and how, well, it looks extremely expensive to collect, and it requires a lot of detail. So I can see it, like you're showing us Chicago, which has an excellent transit authority with, like, and some cities are very good at this. Most, I imagine, are resource constrained, especially, let's say, outside the US.
Mm-hmm.
So what do you do about it?
Yeah, so I would say first of all, for any model we develop for a specific city, we work with local organizations. So that's we rely extensively on MPOs, Metropolitan Planning Organizations, to provide us with the data we're looking at here, right? Every city in the US that is more than 50,000 people has to have, to some extent, some data being collected to look at their overall transportation system analysis. They do not have, like, some of the behavior or some of the computational efficiency or some of the capabilities we have in Polaris. But, when we go to, I'll pick an example, right? Like right now, we've been working on developing the model for Seattle. What we do is we work with local partners, in that case, the University of Washington, and local entities that have the data. So Seattle MPO is providing us with all, like, I would say 80 or 90% of the data you're looking at here. The MPO will provide it to us. All the network, that's provided by the MPO. Traffic controls, the transit network data, that's GTFS. That's publicly available. We do have on the buildings, we acquire a license that has all the information on all the buildings in the US. So we can get it from there. The vehicle information, again, we have a license with all the distribution of the vehicles on any cities or metropolitan area in the US. So, we can have, I would say, a working model probably right now within 3 to 4 months on a new city, pending that we have a good collaboration with local partners. Now, your point is what happens overseas. Overseas is a little bit different, but again, a lot of the model we've developed, so we're developing right now a model for Sydney in Australia. We started to work with Seoul in Korea, Beijing, China, and also looking at some cities in Europe. It's all about finding a local partner that has connections for data access. The data is what we've seen in most cases available. maybe not in some countries. That's like the third pot. But to a great extent, a lot of the data is available as long as you know where to find it. And the key is having local connections. With, let's say, University of Washington, we work with transportation research experts over there that have long-term relationship with local MPOs. So they trust them, they share the data, and we can pretty quickly develop a model. So it is not it's not as expensive as one might think, especially once you develop a process to integrate publicly available data and combining that with some data that can be acquired via licensing.
Okay, and then how do you know if it's wrong? I'm thinking like the
Yep.
less difficult ones, like this road is rated at 35 miles an hour, but even without traffic, it's garbage asphalt, so nobody goes 35 miles an hour. And of course, the trip generation, the surveys are biased, the really challenging stuff.
Yeah, so all good points. So Polaris is a mesoscopic traffic flow simulation, right? So that means that what we're looking at is millions of agents moving over 24 hours. This is not a microscopic simulation. Microscopic simulation, if you have I don't know, 10-mile roads with a couple of intersections going along, right? You can look at impact of asphalt if that particular node or road link, has some issues because there's lots of holes there. Polaris, because of all the roads we're modeling, like the Chicago model includes part of Wisconsin, part of Indiana, and half of Illinois, right? It's like we say Chicago, but we model lots of small towns in cornfields. So we will not validate, and that's not the goal. We will not validate, a particular section of the road as a couple of potholes, and people know about it and they're driving around it. That is not something we would consider in Polaris. What we would consider is making sure that our congestion and traffic flow on an average day is consistent with some of the data the city is providing and other partners are providing. So in that case here, the city is providing us, Chicago DOT is providing us with a lot of information on from traffic light signals on vehicle speeds across many arterials. And so we're using this to have a representative average speed per link throughout the day, right? So what happens in the morning during rush hour, what happens during the day, what happens at night, and make sure that we have, on average, let's say in Chicago Central Business District versus West Side or North Side versus the suburbs, that we actually do have representative average speed throughout the day across the network, not validating single individual nodes between two stop signs or between two traffic lights, if that makes sense.
That makes sense. Yeah, thank you.
Okay. So the way I think about it sometimes like a mesoscopic traffic flow model versus micro simulation. Right here we're modeling water going through a pipe, where the micro simulation will be droplets, one at a time in a very teeny tiny area, right? So we are looking to some extent at individual vehicle behavior on the traffic flow, but to a greater extent, the overall traffic flow is what we're looking at, not the individual vehicle behavior, because that would be macrosim. And the last set of inputs is on the transportation system control, right? So more and more what we see centralized control. Let's say on the highway, when there is an accident, you make closer lanes, you tell everybody, go on the left lane. When also you're on the highway, sometimes there is some information that there is an accident ahead, maybe 10 miles from now, and some people will be like, okay, I'll take the next exit because, I want to avoid traffic. Some people say, no, I'll stay and I'll, stop because I think it's better for me. So anything that is related to overall transportation system control and management is also what something Polaris includes. So when we are looking at Polaris use cases, our four main use cases, and again, growing, but our four main ones are Chicago, Atlanta, Detroit, and Austin. We work very closely with local planning agencies And one of the reasons why we do that is when we look at the impact of technologies, because every city is different, the impact of every technology or policy is different. So when we run scenarios, we run the same scenarios across all cities. So we understand the pro and cons, or what technology or policy makes more sense where and why. We've also I've done a lot of detail work in Ann Arbor because of, they were very active on connectivity and automation, working at Illinois, Beijing, Sydney, and as I mentioned, working on multiple additional ones, so Seattle, Washington, New York, Los Angeles, and I'm sure I'm forgetting a couple of other ones. And in every case, we do work with local partners to implement data and to develop and validate the models. So that was on Polaris, right? So Polaris allows us to consider mobility. Now, when we're looking at impact of technology and policies, mobility, vehicle miles travel, vehicle hourly travels, is just one of many metrics. We also want to look at energy. We want to look at greenhouse gases. We want to look at a lot of other metrics. So in order to be able to do that, we've actually integrated Polaris as part of a complete smart mobility workflow, including like autonomy for energy consumption, which is one of the tools I discussed in November, GRIT for greenhouse gases, which I believe this group had a presentation in December, into a coherent workflow. So what it means is that now we can look at different scenarios: electrification, connectivity, automation, land use, fleet composition, with different policies, different goods movements, different demand, let's say, both on the passenger travel, but also on the freight travel, and all integrated into a current workflow. That means that when we're looking at the impact of technology and our policies, we are looking at all metrics at once. So how is that Polaris workflow unit? So a couple of unique aspects are related to Polaris itself. It is a full feature activity-based model, right? That includes freight shipments and local deliveries all in once. We have the supply and demands that are fully integrated. It's not a back and forth, it's fully integrated. So integrated demand, network assignments, and traffic flow. We have high fidelity vehicle energy consumption model. A lot of these tools usually say I have an average vehicle energy consumption of, let's say, X kilowatt hour per mile for electricity. This is not what we have. We actually simulate many different cars: small, big, medium, old, new. That allows us to have really good energy consumption estimation. We model charging network, including queuing. So we have different type of charging stations: fast charger, low levels, for passenger car, but also for freight. So if a truck arrives at the depot and another truck is plugged in, that truck will have to wait. That will delay the next delivery. And that actually one of the reasons why a lot of fleets right now will tell you that EVs or fuel cell are not a one-to-one replacement for conventional vehicles, for conventional trucks, because of their operational impact. And so we do take that into account. We also look at the impact of land use. So 5 years, 10 years from now, right, population grows. It grows in some cities like Austin, maybe stays the same in others like Chicago. But at the end, behavior, and technologies will impact where people live. We already see that with COVID, and it's only going to get, more important from there. So it is now on the computational side, it is a C++ code base. Some of the
one question about abilities. So you had a connection between urban sim and land use and the resulting impact on transportation.
Yes.
But you did not have an arrow from transportation to the subsequent decision about where people live, at least in your previous.
So they are both. They go both ways.
It is both. Okay, good.
Yeah. So the way to answer a specific question, the way we have the linkage between urban sim and Polaris is that we will start running Polaris to provide all the information for urban sim at time 0. Mm-hmm. Now urban sim will say, now we can run 4 or 5 years of urban sim and say, well, this is how population increase, how land use increase, then we provide that information back to Polaris. Polaris will run for year 5. Then the output of Polaris will come back to Urban Sim. That will run 1 year, 2 year, 3 years, and then after 10 years, that provides the input back. So when we're looking at evolution, it's evolution almost on on a yearly basis, and that is one way. And I'll show you an example where we've actually been able to see the impact of ACC, so automated cruise control. We did that for Austin, as to actually how the increase in ACC market penetration led to a significant change in land use, where people moving further away from where their work is. Now, to take that example, right? So again, closed loop there, but continue on that example, is that, well, what happens if we put a policy in place to actually incentivize people to live closer to their place? So like this, we have the benefits of having a more efficient vehicle from the ACC on a per mile basis, but we don't have the drawback of having a higher vehicle miles traveled. And so we've actually shown that this is possible. So again, it's like taking into account advantage of technology. I have a vehicle that is more efficient on a per mile basis, but at the same time implemented policies to mitigate some of the potential negative effect, which in that case would be like, instead of living 20 miles away from work, I'm going to live 40 miles away from work.
Right, makes sense.
Okay. So it is a very efficient code base written in C++. Again, some of the tools out there are Java, which makes them a lot slower. The tools out there have like, usually 5-10% of agents simulated. So if you have 4 or 5 million agents, you do not simulate all of them. You simulate a sample of them. There is some paper that actually show that any simulation with less than 50% is actually significant issues. We simulate 100% all the time. So despite simulating all of our agents, because we have a C++, we are, I would say 5 to 10 times faster than other codes. So that what that allows us to do, it allows us to do a lot more runs. When we talk to local MPOs, they do have sometimes like the big ones, some agent-based. They tell us they're not using them because it takes 3 days to run one scenario with 5 or 10% of agents. It takes us hours to run 100%. So now we have MPOs coming to us and say, well, we would like to use Polaris to help us with our greenhouse gas planning, because we can run hundreds of simulations where they could not run one.
So then at this point,
yes,
you say optimization. Are you talking about, there's 2 modes. One is you have the most efficient assignment of traffic to roads, like a MatSim scale model, or you're talking about like design of the network, design of policies, that level of optimization? So
we're doing both. So some of the optimization that we will do even before simulation, right? So for example, where should EV charging station be located? How many should they be? Where should they be located? How big should they be based on the demand? If we have some freight that needs to be delivered tomorrow, and we know that a specific depot has a specific number of trucks with a specific number of packages, what is the most efficient way to deliver these goods? So these are optimization we would do prior to the simulation. Now, there are some optimization that we do during the simulation, and eco routing, for example, would be one of them. One of the main challenges of some of the eco routing processes right now, and I'll not even say algorithms, but processes, is that the energy estimation during this optimization is very poor, in my opinion. And my background, I've been doing vehicle system simulation for my entire career. And a lot of them are overly simplified because of computational issues. And as a result, the, I would say, uncertainties introduced by these energy consumption models is too large for them to be trusted. And I'm happy to be proven wrong. So what we've done over the last, I would say, 3 years is develop some machine learning model that are dedicated to energy consumption estimation specifically for eco routing. And so that is trained on tens of thousands of high fidelity energy consumption models. We have a pretty good model right now. We're not there yet, but I believe that level of fidelity, I'm convinced that level of fidelity is required to have a good estimation of the impact of energy consumption from routing. 1 or 2% gain from an eco-routing algorithm, to me, is within the noise, especially with the models being used right now.
And then optimization of whole policies, it sounds like you could do many runs, like efficiently.
Oh, yeah, yes, exactly. So we've looked at one study on having people pay to enter some specific areas. New York is looking at it. Austin is looking at it. Actually, Austin, some extent, implemented some of them, right? So how do you set them up in terms of price to make sure that, one, it does what it's supposed to do, and two, you minimize the impacts on underserved communities? Yes, these are many different runs, and like Polaris is fully deployed on Linux HPC clusters. We're also running on Windows. But right now, our go-to platform is Linux HPC for the reason, right? Is doing one run is computationally intensive, but we're now looking at hundreds of scenarios, and each scenarios, to be able to do it properly, requires many runs, right? So it's I don't want to give here like 4 to 6 hour runtime for 10 million. That's one run, but because the way the model is done, right, we need to do 10, 20, 30 runs sometimes, so we have a good understanding of what the impact of a single scenario is, just because it is stochastic.
Thank you. Makes sense.
Okay, let me go through some examples of studies, so you have an idea of what we've been using the workflow and the tools for. So the first one is looking at transit optimization. What we did here is we worked with CTA, so Chicago Transit Authority, as well as others, and look at the impact of increasing bus frequencies, as well as adding new bus rapid transit lane to increase transit experience, and as a consequence of it, increase transit ridership. So, and the idea here is, how do we get the most bang for our money? So we have in the bottom, like the change in operational cost versus the change in ridership, looking at some optimization. So so this is one way to increase transit ridership. Another way to increase transit ridership is to subsidize first mile, last mile rideshare services. So this was working with Austin, UT Austin, and the Austin area. And so what we've seen here, we started with free, and then regular. At the end, we ended up with maybe something like 50% subsidies. But the idea here is that we can have significant increase. And you say 4.5 to 5% is not a lot, but 0.5% when you have a lot of riders is actually significant, because every single one of these riders, you take a car off the road, right? So here you potentially remove about 100,000 auto-based trip by providing some incentives on first mile, last mile. And Austin is not known for a large transit area. So if you think about what could be done in areas like San Francisco or Chicago or New York, which is something we're looking at right now, that could be significant. We also are looking at example of technologies. So here we're looking at connectivity and how it can mitigate delays caused by traffic incidents. So here, what we're doing is that once we know that an incident is occurring through roadside units, then that information is communicated to the connected vehicles, and as a result, they enable rerouting. So this is not about optimizing traffic flow. This is really about optimizing information and communication, and providing individual agents, or in that case here, drivers, whether they're passenger car or freight, to reroute on the fly when incident occur. So we do have the ability to integrate accidents or any specific events like road closures, whether they come from incidents or whether they come from floods, traffic, roadworks, things like that, into Polaris, and then here quantifying what happens to the overall traffic flow. Now, some interesting here is that the best performance is achieved at 50% penetration rate. If everybody knows everything that's going on all the time, they all tend to take the same route, which then creates some other problems. Because again, we do not have an overall system level control. We're just providing the information to the agent. So if you tell people, everybody, there is an accident there, then everybody wants to reroute, and then that creates some other issues. We also been looking at the impacts of level 2, cooperative adaptive cruise control, so partially automated vehicle, and how they compare to level 4, more like hand-free driving in terms of I don't know why it's with looking at value of travel time here, VOT. So what we see is that if people have a partially automated vehicle, they still need to pay attention, right? So they actually don't tend to drive that much more. Now, if you give people kind of, I told you, it's like I can go on the highway and press a button, and I really don't have to pay too much attention, even if, trust me, people should, or they tend to drive a little bit more. So what it means is that people tend to drive more. That slows everybody down. Your vehicle speed goes down on the average. If your vehicle speed goes down, your energy consumption goes up, greenhouse gases goes up, and so on and so forth, right? So that's where we make it easier for people to drive. Well, guess what? They'll drive more. And if they drive more, they make the whole network worse. So
let me ask you about that one.
Yeah.
Automated vehicles can, in principle, I guess, work with each other, but it sounds like you're not including that.
So on that particular study, we did take into account the fact that connected vehicle make their surrounding vehicle better. So we have different traffic flow or congestion patterns that occur because of I would say after you reach a certain level of penetration.
Mm-hmm.
So if you have like 5 or 6% of connected vehicles, you're not going to make the surrounding vehicles better. But if you have like 35, 40%, you actually can make everyone better. So there is some surrounding benefits. So that's just even without talking about vehicle to vehicle, vehicle to infrastructure. Now we do have in other studies I also added the fact that here the vehicle are on their own, right? They're just like I am my own bubble. But we have integrated the fact that we consider now vehicle-to-vehicle communication that also will impact traffic flow. We've also, because we model traffic light signals and we have, I'd say significantly upgraded in the last year our traffic flow, we now have a vehicle-to-infrastructure, so vehicle talking to traffic light signals, so that it also impacts the traffic flow. So at an aggregate level, at a mesoscopic level, right? We have other tools to do very detailed vehicle-to-vehicle, vehicle-to-infrastructure benefits. But when you're looking at millions of people moving together, we do take into account vehicle-to-vehicle and vehicle-to-infrastructure. But again, it's at an aggregate level, really looking at the impact of traffic flow on the road link node.
Okay, and then let's say we have a significant penetration of self-driving vehicles. How is it different from buses? Because I'm saying, like, obviously a bus that's full is far denser than a lot of self-driving vehicles. But most buses are not full on a large fraction of their routes. So in the end, you're getting a lot of self-driving vehicles that are just caravanning. How is that different from buses?
So we did a study, I would say 2 or 3 years ago on driverless vehicles. We have not, so our sponsor DOE right now, maybe background before I come back. So about 3 years ago, there was a lot more interest from our sponsor in DC and our stakeholders into driverless vehicles. So a lot of the work we've done was on that. Over the last 2-3 years, we focused a lot more on near term, i.e. 10, 15 years. So a lot of what we've been doing is partial automation and with connectivity. Now, to come back to your question, and you're right, transit buses, I believe on average are about 6 to 7 passenger, so not 50, but it's still more than one, right?
Right.
And what we've seen when we're looking at driverless, significant penetration of fully driverless vehicle, that unless you have a really good optimized system, you end up in a very precarious solution where you have a lot of empty miles, significant amount of empty miles that are generated by the driverless vehicle. So the worst case scenario is driverless vehicles are affordable for individual households. That means that, let's say you have 2 people in the households that own one driverless vehicle and they have a kid, right? So in the morning, you'll have your driverless vehicle drive your kid to school and come back to the house, because then it has to take you to go to work, and then you come back to the house because then you have to take your spouse, let's say that, works from home now, but at some point wants to go to grocery store, and then it comes back to the house. And then the vehicle, has to drive empty and pick up your kid from school, drive it to the house. And then the vehicle has to leave empty and pick up me at work and come back to the house. So you have a lot of empty miles. That's like literally worst case scenario. Driverless vehicles are affordable. If driverless vehicles are not affordable and are expensive and people want to share them, well, then you need to have really good optimization to actually be efficient. And there's many reasons for that, but the primary one, in addition to empty miles, which still remain important, is the fact that the electrical consumption required by the computation within the vehicles, signals, sensors, GPUs, so on and so forth, is significant. Right now, my understanding from what we hear from the OEMs, it is about a 3 to 4 kilowatts. So just to give you an idea, an average mid-size car vehicle driving in a city needs 7 kilowatts. So you're adding 4 to 7. And air conditioning is about 800 watt to 1 kilowatt. Again, 4 air conditionings running all the time. Now, there's a possibility that in 10 years from now, this 4 kilowatt become much smaller. And, they will. It's just, it's how much. And again, people are talking about 750, 800 watts constant load. That is a significant load. That's still 10%. So you have to be at least 10 to 20% more efficient using these vehicles so that you are zero, right? Compare an energy consumption compared to a vehicle. So significant challenges. If the system is very well optimized, potential opportunities, but I would say the potential of having increased energy consumption due to significant empty miles combined with much higher electric loads is significant for driverless vehicles. From the studies we've been running, where I think we had like 30 or 40% market penetration, so significant market penetration. We did not end up in a good spot.
So things like private or municipal taxi fleets that are optimized by their operator sounds like it's the better way to go.
That if you have driverless, I think we need to move away from personal ownership to have any chance to reach some of the targets in terms of energy and efficiency.
Okay, makes sense. Thank you.
Maybe one or two more. I think we have 5 minutes left. So this is just an example of land use where we actually use Urban Sim along with Polaris and the workflow to, again, look at the impacts. Well, if we make it easier for people, and at some point in time, right, they live in a dense populated area in a condo, or they rent a house and they want to buy a house, where do they move? How far do they move? Well, maybe they would have moved in the suburbs anyway, at 10 miles away. But now, because you have level 4 CACC, you're moving 20, 30, 40 miles away, right? So again, VMT is key. You decrease congestion, people will drive more. You make it easier for cars to drive, people will drive more. So how do we actually make sure that we enable people and goods to go where they need to go and where people want to go, right? Because we definitely want that to happen. but at the same time, take into consideration the system. And as I mentioned initially, right, if we see that there is a potential for people moving further away, increasing vehicle miles traveled, well, maybe there is some policies that can be implemented. So like we work with EPA here to actually implement a CO2 pricing policy so that, you know, we have the benefits of CACC, but at the same time, avoid the increase in, or minimize the increase in VMT, because people will still be okay paying for it. But you know, we're trying to counteract some of the VMT increase, value of travel time impact from the technology, so that the system overall is much better. Equity is, major focus has been, and is even more now. Again, we know we have a description of every household, very detailed. How many people, where do they live, where do they work, what's their income, gender, age, again, based on the statistical representation of census data. That allows us to look at the impact of policy. Like here, we're looking at change in travel cost per $1,000 income if road pricing was to be implemented in different cities, looking at Chicago here and Detroit. So Chicago, right, west side here of the city, is, underserved community. So, we see that it actually would have a significant negative impact on that part of area. Same thing, south side. Not a lot of impact on the north side. Again, this is where affluent communities are. I was saying, I guess, last slide, and again, there's more examples, and there in our share presentation, we obviously are looking at vehicle electrification, including charging station location. A lot of the tools right now looking at EVSE are looking at average. We actually know where parking lots are. We know where depots are. So we have very detailed information where we can say this is not just where the charging station need to be based on how people drive in that particular roads or that particular zip codes, but this is where potential public charging stations could be located, parking lots, grocery stores, so on and so forth. So again, a lot more granularity because we know we have a lot more information on the system itself. So I'll stop here. If you have any questions, we have a couple of minutes left. We'll share the presentation. You have my email information. If you have any questions on any of these and much more, please let me know. There is a series of webinars that are coming up that will dig into a little bit more of some of the insights and lessons learned. But I understand that you're also interested into developing your own algorithms and doing your own studies. And that's something that we would be happy to discuss further with you on how we can support that.
Well, thank you very much. In fact, let me ask you one last question on that. How much more effective would these models be if you have live data or fine-grained mobility data or anything like that?
Yeah, so we've started a couple of projects to look at how live data could be implemented. And so there is two usage for the tool, right? The one is like, what can we do today to improve today's technology? And live data would be very helpful to make sure we can have that. Let's say because then you could feed that into some logic to directly impact some decisions in a traffic flow, traffic signal management center, for example. Now, a lot of what we do is like what happens 10 years from now, 15 years from now, 20 years from now. If policies are in place and I have a lot of electric vehicle and I have a lot more freight deliveries and a lot more people stay home and well, in that case, right, so a lot of our use cases are like 2030, 2040, 2050. So that's where a lot of our focus is, because that's what our sponsor is, DOE or DOT, right? So they're looking at long. Now, if you're looking to MPOs and local DOTs, yes, they are interested into, can I put in my data now? Because that helps me make decision now.
Right. It makes it,
yeah, different stakeholders, but yeah, it's definitely, I don't think you'll ever hear any one of us on the calls like say that is bad. It's just different usage.
Yeah, got it. Well, yeah, thank you very much. That's fantastic.
All right, thank you so much.
Have a great day.
You too. Bye.